Dr. Jinyan Zhao is a postdoctoral scholar and a software developer at NHERI SimCenter at UC Berkeley. He completed his PhD in structural engineering mechanics and materials at the Department of Civil Engineering at UC Berkeley. Dr. Zhao is currently developing and benchmarking research capabilities for regional scale risk analysis resulting from natural hazards. And he's also adding geotechnical perspective to SimCenter. Um, Dr. Zhao, thank you again for joining us. I'm going to stop sharing my screen and allow you to share your presentation, if that's okay with you.
Sure. Thanks, Richard, for introducing, and thanks a lot for inviting me here. It seems,
Absolutely.
let's see how I can share my screen properly.
So we are seeing the
All right,
procedure. Oh,
this is
perfect.
the presentation. Thanks. All right, so it's a great pleasure for me to attend this meeting and share some of my experience at SimCenter. And the topic of my presentation today is Introduction to SimCenter Tools with a focus on R2D, which is the SimCenter software that I personally worked on a lot. And I also want to talk about how you can potentially use SimCenter tools to help your research. I think everyone knows what NHERI is, and many of you might have worked on one of the experimental facilities or the reconnaissance facilities. And besides them, we have SimCenter as a computational modeling and simulation research facility. So different from using experiment and field observations to understand natural hazard phenomena, at SimCenter, we aim to use simulation to understand this phenomena. Say I have a reinforced concrete moment frame, and I want to understand the behavior of it, and there are some different combination of structural configuration or material property. And I also want to understand to estimate a probability distribution of the base shear at different level of deformation level. It's not possible for me to build 100 RC frame, put it on a shaking table and test it. It's a huge waste of money and a huge waste of time. So this is when SimCenter software QualFAM can come in and help me out. In QualFAM, it can take a structural analysis model, generate a number of samples of this model input using Monte Carlo simulation method, give the input samples to the model, collect the output, and study the statistical distribution of this system response. And in uncertainty quantification, this procedure is usually called forward propagation. Many of you may think forward propagation, Monte Carlo simulation, these are simple. I can do it with a piece of code in a snap of finger. It's easy. And I believe you can do so because I did something similar in my PhD also. But QualFAM can allow you to a lot more than just forward propagation. It can allow you to do sensitivity analysis, reliability analysis when you are dealing with rare event simulation, surrogate and reduced order modeling when you want to reduce the computational time of your simulation tools. And also it allows you to perform Bayesian and deterministic calibration of your model against experimental data. QualFAM is powerful, and it is one of the most popular software that SimCenter has developed. So far, it has thousands of active users and is cited in journal publications many, many times. So as I said, QualFAM is powerful, but SimCenter has more. On this plot, you can see a hierarchical level of the 7 desktop applications that SimCenter developed. QualFAM is at the bottom. It's the foundation of all the software, and it is used for general purpose uncertainty quantification and optimization. On top of QualFAM, we add in hazard-specific modeling perspectives and created 3 hazard-specific structural response software. Namely, for earthquake engineering, we have EEUQ. For wind engineering, we have VUQ. And for hydro applications, for water-related natural hazard, we have HydroUQ. Taking the earthquake engineering application as an example, when we do a seismic risk analysis, a lot of times we want to construct a response spectrum, and then we select ground motion records to match those spectrum, give the records to a structural analysis model, perform some nonlinear time history analysis, study the structural response in those analyses. And to help you to facilitate this whole process, in EEUQ, we have the response spectrum construction algorithm and also the ground motion record download, selection and download algorithm functionality embedded. And this makes the whole workflow much easier than it was before. And for wind application, we have a computational fluid dynamics, CFD replication of wind tunnel. It helps you to estimate the wind sequence at anywhere surrounding your building. And you can use that as an input to your structural analysis model. In Hydro UQ, similarly, we have tsunami and storm surge related modeling functionality embedded. These three softwares gives us structural response under natural hazard events. And those structural response are usually measured as engineering demand parameters, EDPs. And these EDPs are usually interstory drift and floor vibration. But when we make decision, we want something more straightforward. And this is when, the next software performance-based engineering computations comes in. This software PBE allows us to do a so-called damage loss analysis, where we estimate the damage measure, say damage state 1, damage state 2 of the structure using fragility curves. And then we also estimate the monetary loss and time loss using consequence functions. And on top of PBE, there is this regional risk assessment software, R2D. And R2D will also be the focus of the rest of my presentation today. Here is a user interface of R2D. It can be used to study multiple types of hazards, namely earthquakes, hurricanes, tsunami, storm surge. It can also study multiple types of infrastructure assets, including water pipeline network, buildings, and transportation infrastructure. In the user interface, we have the open source GIS software, QGIS, embedded, so we can manage this spatially distributed data in a relatively easy manner. And in R2D, we also tried to create a flexible workflow, so you can select from different assessment methodologies that you would like to. Looking at this, you may be surprised and confused. At least the first time when I look at this, I was shocked. I wonder how a single software can do all of this complicated tasks. But after working for SimCenter for over a year, I got my question answered. And in the next few minutes, I will try to explain to you how R2D does all of this step by step. On the left-hand side of this slide, you can see a regional simulation workflow in R2D. And everything starts by defining the asset inventory that you want to analyze. For example, I want to do an earthquake building assessment using famous hazard fragility curves. To do that, I will need to know the build year, the number of stories, the occupancy type, and the structure type of all the buildings in the region of interest. And differently, if I want to use OpenSys model and multi-degree freedom model to simulate the buildings, I will need to know more. I will need to know the story height, the story stiffness, story damping, and etc. For hurricane applications, we need a totally different set of information for the buildings. If I want to use famous hazards methodology again, I will need to know the roof shape, first floor elevation, land cover type, and many others. And if I want to do a different type of assessment, I will need the specific attributes I need to model the buildings and analyze the buildings. To collect this inventory information is not simple. It's quite labor intense. But once you complete this, I think you have conquered the hardest part in this regional simulation. So after defining the asset inventory we want to study, we need to define what hazard we want to study. Again, if you want to study buildings in earthquakes using famous hazards methodology, you will need a field of the ground shaking intensity measure and a field of the ground failure intensity measure. In R2D, we have a toolbox to help you to estimate these intensity measures using ground motion prediction equations, spatial correlation models, and some simplified landslide and liquefaction models. And if you want to perform time history analysis, using OpenSeas, you will need the ground motion records. You can select ground motion records using R2D, the same toolbox. And the better way, maybe you can go download some regional ground motion records from those physics-based ground motion simulator database and use them, import them in R2D and do the subsequent analysis. For hurricane applications, again, if I want to use famous hazards fragility methodology, I need the peak wind speed. In R2D, we also have a tool to estimate this wind speed. And if I want a higher resolution analysis, we need the higher resolution intensity measure for the wind and water problem. R2D doesn't support you to do that so far. You can do it, but you can do that with another software and import the data, the output of the other softwares to R2D and do the rest simulations seamlessly. After defining the asset and hazard we want to study, we need to select how we want to model and analyze the infrastructure in the region. The built-in options in R2D are multi-degree freedom models to simulate buildings, and the intensity measure as engineering demand parameter method. The IM as EDP method is used when you want to use those fragility curves who directly map from intensity measure to damage measure. So you use IM as the EDP in your as the input to your fragility curves. These two options look boring, so we also allow you to define your own structural modeling and analysis engine. You can essentially just give us a Python code, use that as a wrapper to any structural analysis engine, and use that in your regional simulation. Another option is you can create some surrogate models using QuOFA and import those surrogate models to R2D and do the rest analysis on a regional scale. This modeling and analysis procedure tells us the engineering demand parameters, and the next step is to perform this damage loss analysis to get damage measure using fragility curves and monetary and time loss using consequence functions. In R2D, we have the famous hazards fragility curves and consequence functions built in. They are ready to use by clicking a few buttons. And you can also use your own fragility curves. What you need to do is simply prepare a CSV spreadsheet containing your fragility curves. Each row is one of your fragility curve. And also you need a short Python script to match these fragility curves to its corresponding buildings. You only need these two input, and in R2D, we can do this regional simulation for you. The final step in the regional simulation workflow is system performance and recovery. This is something we are working on developing. They are working through our backend code, but they are not readily available through our user interface now. And the system performance, one of the system performance we are working on is this traffic flow simulation, where we implemented a dynamic traffic assignment algorithm to estimate the travel time of all the trip in the region. And we can also estimate the congestion level of each road in the region. Another system performance tool we are developing is this water network hydraulic simulation, where we can simulate hydraulics and water quality delivery after defining the disruption and the response and mitigation after natural hazard events. Using this, we can quantify which area may go out of water service and how long this outage will last. And the third system performance simulation functionality we are building is this community recovery simulation methodology. It is used to quantify the recovery and functional resources demand and supply of each infrastructure component in the city, and it can also simulate the flow of those resources among different infrastructure layers, such as water can flow from water treatment infrastructure to buildings, and electricity can flow from power grid to buildings. And after defining all of this methodology can help us to estimate the recovery time and quantify the resilience of the whole community. I have an example to elaborate more of this in my later presentation. But here is a summary of the workflow in R2D. We start by defining asset, defining the hazard, select modeling and analysis methodology, select the damage loss methodology, and perform some system performance and recovery simulation in the end to quantify the overall regional resilience. To give you a better sense of how exactly R2D works, I prepared two examples today. The first example is a community recovery simulation of a community in the Bay Area, in the San Francisco Bay Area, after a magnitude 7 earthquake event. In this example, I used R2D to estimate the ground shaking intensity in the region, represented by the PGA on the left-hand side of the plot, and I also estimate the liquefaction-induced ground failure, ground deformation, as presented on the right-hand side of the slides. And then I map those intensity measures to all the infrastructure, use famous hazards method to estimate the most likely damage state of all the buildings in the region and all the roadways, bridges, tunnels in the region. Using this, I defined the restoration curve for all the components. I also defined what's the recovery resources needed by each of those components. This recovery resources includes money, labor, engineers, contractors, and I also define how to distribute these resources among the infrastructure. In this example, the transportation infrastructure gets a higher priority than buildings. So that these resources will be distributed to the transportation infrastructure first to recover the roads and then recover the buildings. After doing this, on the left-hand side, you can see a result of this regional recovery simulation, where I have an estimate of the recovery time for all the components in the region. And on the right-hand side, we can also study what's the total supply and demand of shelter in the region. The total demand in the region is represented by the orange horizontal line, and the total consumption, which overlaps with supply, so you couldn't really see. But in this plot, the green curve stands for the supply, the shelter supply and shelter consumption in this region. And looking at the difference between the demand and supply, this is the total unmet demand. In other words, the shortage of shelter in this region after this earthquake event. So using this simulation, this kind of plot, we can study how much temporary housing we need to prepare, we need to provide to the city so the shelter demand can be met by all the citizens in the region. Using a similar plot, we can also study if there is a shortage of repair crew for buildings and transportation infrastructure. As I said, transportation infrastructure gets higher recovery priority in my example, so they recover faster. And it also sees a very small shortage of repair crew. However, the buildings experience some shortage of repair crews. So if we can allocate more worker, more labor from other regions, we may have a faster recovery for this specific example. And this plot is the status of all the infrastructure components at different time steps after these earthquake events. I'm just showing this to show you that we have a very high resolution simulation of all the status of the infrastructure along the recovery process. And this generates a lot of data, and you can do a lot of post-processing and study many interesting effects in community resilience. So that concludes the first example I want to show you. In the second example, I studied the same earthquake event, but I looked for the disturbance of this event to the San Francisco Bay Area transportation network. Again, the first step is to estimate the ground shaking intensity for the whole San Francisco Bay Area region. I did that in R2D, and then I analyzed the possible bridge closure, roadway closure, using this PGA as input and famous hazards methodology. After that, using the traffic flow simulator, the dynamic traffic assignment algorithm, we can estimate the congestion level before the earthquake and the congestion level after the earthquake. And comparing them is a bit difficult on these two moving plots. So I take a snapshot of the congestion level at 8 a.m. in the morning rush. And you can see after the earthquake, there is a lot of congestion on the east side of the Bay Bridge. And there is also a lot of trips as to detour on the east side of the San Francisco Bay Area. I also compared the disturbance of this -7 earthquake event on the Hayward Fault with another earthquake scenario with the same magnitude. The second earthquake scenario happens on the San Andreas Fault. The San Andreas Fault is on the west side of the San Francisco Bay Area, so it goes across essentially downtown San Francisco. And because the spatial distribution of these two faults are different, you can see a different distribution of the damaged bridges and the closed roads in these two earthquake events. And subsequently, they also resulted in a different distribution of traffic congestion. And when I look at the statistics, I found that in the Hayward Fault scenario, more trips are delayed, and the average delay time and the average time increase for all the trips is also higher in the Hayward Fault scenario. So in a nutshell, Hayward Fault caused a bigger impact to the performance of the transportation network in the San Francisco area. And I looked into it and I wondered why. So I figured that I was simulating the traffic demand in the morning rush hours. And in the morning, a lot of people are traveling from the east side of the Bay Area through the Bay Bridge, get into the downtown San Francisco, and they work there. So when those bridges are closed, this caused a lot of delay of the trips going from east of the Bay Area to the west of the Bay Area. And this explains how the Hayward Fault may be the dominant risk source for the transportation network in the San Francisco Bay Area. So that wraps the examples I would like to show you. I hope that give you the sense of how R2D can work. And now I want to share some of the thoughts that I think R2D may help your research. One method I think R2D can help your research is it can really help you to scale up your models from a local scale, a single building scale, to a regional scale. In the research of many of you, perhaps you develop some new fragility curves for some sort of infrastructure, buildings, bridges, lifeline systems. And you may also develop advanced numerical models. And some of you also develop corresponding surrogate models. And some of you may develop new hazard models, estimating wind field for hurricane, or estimating the runout resulted in landslides. So using R2D, you can really scale these models to a regional scale and study the impact of your model to a much broader community. A second idea that I think you can use R2D in your research is R2D can help you to generate data to supplement proof of concept, validate your model and algorithms. No matter you have a computer vision model to generate inventory data, or you have a smart sampling algorithm to efficiently quantify the uncertainties and quantify risks, you can use R2D as a testbed and to prove the concept of your methodology and perhaps validate your methodology. And in the end, we can also use R2D to understand the nature of natural hazards and community resilience. Perhaps you are developing new major metrics for community resilience and social equality. And perhaps you are studying what's the dominant factor to building safety on a regional earthquake event so we can build safer houses. Using R2D, using the data generated in R2D, this can save you a lot of time to generate the data by yourself. You could just use the data and study them and complete your research goals. But what if I have a wonderful research idea and the R2D doesn't meet my need? A possible answer is you can extend R2D. So all of the source codes of SimCenter are publicly available on our GitHub. And most of the codes are written in Python. so they are relatively easy to read and to modify, to extend. And we also have a comprehensive documentation to guide you through how to understand the codes and how to extend the codes. And most importantly, we have a big SimCenter team supporting you. If you have a special needs, reach out to us. All of the SimCenter team will be very happy to support you in your research. And with this slide, I also want to acknowledge that most of the presentations I made today, they are not my personal achievement. They are the teamwork of all the SimCenter team. So all the credit goes to the SimCenter team. And if you'd like to know more, you can refer to our website. There are links to download the software, links to our documentation, and links to join a SimCenter forum. And you can also find us on several major social medias. With that, thank you very much.
Thank you so much, Dr. Zhao. Now I'd like to open it up to questions. If anyone has questions, please unmute yourself and ask away, or you can also put it in the chat. I know Esteban looks like he wants to ask something.
Well, I potentially could have a question. In fact, it's just maybe to see if I understand where does it come from. The functional recovery part of is it based on the last module of FEMA P58, or is user defined? Where did you obtain that information? Because I'm assuming that it depends on the region, and you have a lot of things in there. So is user defined, or are you getting that information from another source?
Exactly. So SimCenter aims to build a framework. We are creating this simulation functionality. We allow the users, if you want to use this functional recovery simulation functionality, you can define what kind of restoration curve you want to use. You can define what resources each building may require in this recovery. And in the example I showed, I referred to Hansa's technical manual. In there, they have some simple restoration curves.
Okay.
Yes, to define the restoration of the buildings and bridges. And there is also a paper published by one of our collaborators. He's at ETH in Zurich. He studied what resources may need for the recovery of different type of infrastructure.
Professor Stoyanovich.
Boja, exactly, yes.
Okay, yeah. Okay, yeah, it looked like that. So, okay, perfect. Yeah. Thank you.
I do have a question about the amount of data that needs to be stored on your personal computer. How does that work?
Yeah,
when you're trying to use SimCenter?
Yeah, good question. But I wondered, are you more concerned on the input data, or are you concerned on the output data?
I'm mainly concerned about the capacity. Most of us run a lot of software. How much data do we need to download in order to use these softwares?
To download the software itself is 1 to 2 gigabyte itself. And if you need some special functionality, for example, you want to use the regional liquefaction model in seismic analysis, you will need some geological database, and those may take some of your storage, but I don't think it will go beyond 5 gigabytes. And for the simulation part, SimCenter tools are connected to DesignSafe. So you can essentially use our interface. You define what kind of analysis you want to perform. SimCenter tools package these things, send the data, and send your command to DesignSafe, run your simulation on their high-performance computers. and then you download data, the results data from DesignSafe. So using DesignSafe and their high performance computer resources, I think, at least so far, I don't see any user running into trouble of dealing with the data.
Gotcha. I guess another question on that for like the travel time simulation, what is the computation time for if I wanted to do it on my personal?
Yeah. For a single scenario, it takes 20 to 30 minutes on my laptop. So we are not dealing with a super high resolution traffic flow simulation. We are using this dynamic traffic assignment algorithm. It's not as accurate. It doesn't capture all the local effects such as traffic lights, stop signs. No, we cannot capture that. But we can capture what's the estimated travel time from, say, one part of the Bay Area to the other part. And this kind of global effect is what we really want to understand in this regional scale assessment. And if you would like to study the local effect, you can pick up a region, do the damage loss analysis in R2D, take the output, send it to another traffic flow simulator. I know some people have done it already. They have a bit higher resolution traffic flow model. They take the output of R2D and study the effect of natural hazard event on their traffic network. So the one that you can find on our GitHub, it doesn't take a lot of computational resources. It's a relatively simple model used for proof of concept.
Thank you so much for that answer. We do have a question in the chat, it seems. I'll go ahead and read it. It was really amazing presentation. Simulation is quite interesting. I'm working in this area of humanitarian logistics management and road traffic and travel time simulation of R2D. Okay, I wanted to know what is the configuration of system we need to run the tool smoothly.
The configuration of the system, I guess for the traffic network configuration, again, it depends on what kind of traffic flow simulation, what kind of this traffic simulator you'd like to use. So far, we only used the relatively simple one, as I said, the dynamic traffic assignment algorithm. But to link R2D to a higher resolution, higher fidelity traffic flow simulator, I don't think there is a big difficulty. We essentially just need to map the physical damage that R2D produce to your traffic network. And then it is you, the researcher's responsibility, or it is you to answer the question how the traffic demand will change. Like after an earthquake, maybe a lot of people, they don't go outside anymore. I think this is a very difficult question to answer, and SimCenter can only support tools to help you answer that, to help you study that. We do not have a very good answer to help you define those traffic demand and some system configuration. We provide tools to help you to study the performance of those traffic network. I hope that answers the question okay. But if I don't, please follow up with me, send me an email. We have some transportation engineer experts in our team. We can provide support.
Fantastic. A lot of good opportunities here. Anyone have any other questions? We're about to wrap up here, running at the 12 o'clock mark, CST. Any last questions? All right, then. Guess not. Thank you so much, Dr. Zhao. Also, before we go, I would like to mention We do have another upcoming meeting. This is a monthly recurring general meeting, and our next one will be on September the 20th, 11 a.m. CST, as always. Thank you so much, everyone, for joining. And I think one round of applause for Dr. Zhao is in order here. So thank you so much. That was a great presentation.